So let's move on to chapter 4, imputation. Okay. So here's a motivating example. So we have x and y random variable. X is always observed, and y is subject to missingness. And so delta is the indicator function. So delta equal to 1, we observe y. Delta equal to 0, we don't observe y, so we use y star. So y star is essentially whatever, right, imputed value. And then what is the minimum, which is the possible condition in order for this imputation estimator to be unbiased, right? So that is the first question we would like to address. So the answer is this condition. Okay. So, and so we have two questions. What is the first one is, what is the condition for imputation estimator to be unbiased? So that's the first question. Second question is, what is the condition to achieve condition 2, right? I mean the equation 2. That's another question. So so let's first discuss how to prove. So here we can first consider yi, okay, just the sample mean, and then the difference between the sample mean is between the imputation estimator and the sample mean estimator is what? So the observed part are all cancels, right? So then the only thing remains is yi star minus yi. Okay. So now we want this guy to be 0 expectation. But notice that delta is another random variable, right? So you cannot really ignore delta. So then perhaps what you can do, so okay, well, so that is this guy, of course. Well, actually, let's move on to here. Right? And then we cannot, so it's a product of two random variables. We cannot make this guy equal to 0. It's impossible, right? So the only hope that we can, so we want this guy to be 0, right? We want this guy to be 0. So that means we want this guy conditional on. So what is the sufficient condition? Basically, how to achieve this equal to 0, right? How to achieve this 0? So the condition is we want this guy conditional on delta I equal to 0 to be equal to 0. So that is the probably the weakest possible assumption. And now, I'm sorry. Sufficient and necessary. Sufficient and yeah. So I think sufficient and necessary. Yeah, right. Okay, because we want this to be for all. I mean for all y. So yeah. And now we need a sufficient condition. So what is the sufficient condition for this? Well, you can see the problem is we cannot really compute the distribution among delta equal to 0, right? Delta, I mean, we cannot really obtain the distribution of y given delta equal to 0 because we don't observe y. at delta equal to 0 by definition. So we cannot really do that, but you can do something like x and delta equal to 0. So if you do this way, and then this guy is equal to y given x and delta equal to 1 on the MAR, right? So on the MAR, delta equal to 0 conditional. So conditional on x, these two distributions are equal. So that means if I make if y star satisfies right? So if y star satisfies this and MAR holds, then basically we get this equality. So that is gives the justification. So that gives an idea of how we actually do imputation in practice, right? We basically on the missing and random, we basically want to find y star such that the conditional expectation is derived from the conditional distribution y given x and delta equal to 1 among the respondent. Okay.
So,
yeah.
Here, does the MAR condition help in anything? So you said that we want to find y star that follows the last equation. So do we need MAR assumption?
So this equality does not, but for this we do need.
And why does that the second last equality? So expectation of y given
Even here or here?
Yeah, here. Yeah.
So this one.
Yeah. Why does that help?
So MAR, what is the MAR in this setup? Y is independent of delta given x. Okay. So okay, that's a good question. So two different. So MAR is in this context is y is independent of delta given x. So that is if in terms of y, right? So regardless of whether delta is 1 or 0. So it's actually 1 or 0. That doesn't change, right? I mean, so that's one way. Another way is actually P delta equal to 1 given x and y is equal to delta equal to 1 given x. So in terms of, so as of, I mean, for y, it depends on x only. So delta doesn't really depend on y once we condition on x, right? Another way for delta, same story. We exchange the order. So for delta, it depends on y only through x. So once we condition on x, it's no longer depends on y. Okay. Let's move on. So that basically take care of the basic idea for imputation. And then so then if you have a linear regression model, so that is an assumption. So if you have a model, a regression model, then we can use respondent, right? We use so basically this is unknown parameter, but we use the cases with the delta equal to 1. Delta I, yi minus beta 0 minus beta 1 xi 1 xi, right? Equal to 1, 0, 0. So you solve this kind of equation using among the respondent only to solve this to obtain beta hat. Okay, so beta 0 hat, beta 1 hat. So that is the solution. Okay. So this equation basically leads to this solution. And so then once you have this guy as a prediction, so that's basically prediction, right? The best prediction. And then you plug it to an of the y. So that is your imputation estimator using regression model. So you can call it regression imputation estimator. And then why we have this one? Well, because of the property of the residual. Okay. So because of the property of the residual, we have this property, right? And so that this guy, summation of this guy among delta one is summation. So basically what I'm saying is here is this guy is equal to 1 to n delta I yi hat, right? And then this is also yi hat. So basically it's just a summation of all yi hat. Okay. And now the main topic of the chapter 4 is how to make an inference. So this is just a point estimation, right? This is just a point estimation. And we statisticians not just be satisfied with the point estimation. We are interested in inference, right? We want to construct the confidence interval and things like that. So that's not the end, right? End of the story. It's just the half of the story. The other half is how to make an inference. So that is not a trivial problem. So that is the basically motivation of the this chapter. Okay, so we'll learn to how to compute the variance of this guy. And so one immediate observation is that your imputed estimator is lone. So you have a, so you can call it imputed values, right? So these imputed values are not IID. Right? So that creates the whole problem. Original data is IID. Right? Original data is IID. So then you can apply central limit theorem and do confidence interval, everything. But this one is not IID. So you cannot really assume that this is IID and you just treat it as the value and compute the confidence interval. Then you are underestimating the variance, true variance. Okay, because they are correlated. So positively correlated. So then we really want to reflect the structure, probability structure in this imputed data set. So okay, so that is the basic bottom line. Now let's move on. So I'm gonna introduce some concept about the estimating equation. So here sometimes So this is the parameter. So theta is the parameter in the parametric model. Okay, right? Theta is the parameter in the parametric model, like a normal or gamma, whatever. But sometimes that parametric model assumption can be too strong model assumption, right? So we don't sometimes we don't really want to make that assumption, strong assumption. We just the parameter. So now I'm going to introduce another parameter psi, which is defined through an integral equation. So this is an integral equation. So for example, if psi is property y less than 1. Okay, so this is one parameter. So what is the meaning of this one? Well, the original meaning of this guy is this one, right? You have something like this f y dy, d mu y, whatever. So this is, oops, well, okay. Okay. And now the problem is if you want to compute this, I mean estimate this particular parameter, right? Proportion. So I mean this could be C. And for example, Y is income and C is the poverty line, for example, right? And if you means what the government maybe count, I mean state government or some developing countries, they are interested in estimating what is the proportion of those people in the nation, what is the percentage of people living below the poverty line, right? So that kind of, so then problem, if you assume, sorry, this is what am I doing here? This is not really correct, right? This doesn't make sense. So what? Okay, density, right? So the problem with this is that we don't necessarily know the true density function, right? So all we want is to compute the if you are only interested in computing this kind of parameter, then probably you just create a function. So estimating function is just indicator of y less than c minus psi. Okay. So then what? If you take the expectation, then the expectation of this guy is equal to this guy, right? So the point is that you don't have to know the true density function to estimate the phi. That's the nice thing about estimating function approach. Okay. So actually I can, so if you write this in one as an integration, so how would you, right? So this is actually, so this expectation, actually in the expectation, it depends on the setup. Some sense, but you don't have to know. So the mapping from theta to phi psi is not necessarily one-to-one. You actually different distribution, different parameter, different distribution can achieve the same, can obtain the same parameter, right? So in that sense, this is a semi-parametric because psi is the parameter of interest, and all the other parameters are completely nuisance. Okay. Well, anyway, nice thing about this estimating function approach is that the constant estimator is very easy to compute, actually, obtain. So you can just, so this is integration, right? So this is actually population expectation of the estimating function. And so you replace it by sample version. So if you write it this way, so multiply, so then this one is one. This one is a sample version of the expectation of the estimating function. Okay. And so this is more general class of the general class of finding estimating a parameter. And now, what is the asymptotic distribution of psi? The solution. Okay. Well, so so you can see that the solution to this, so the solution to this equation, which we call estimating equation, will be written as a psi hat, right? Psi hat n is a function of x1, right? It's a function of n random variable. I mean, sorry, it should be y. Okay, function of n random variable, and we are interested in. So this could be nonlinear, right? So this function could be nonlinear. And then we want to do asymptotic, you want to do establish essential limit theorem and things like that. So then the only tool we know for central limit theorem is for some of the IID random variable, right? So then the idea is for any, this looks very complicated, but the bottom line is, suppose I have an estimator which is a function of x1 to xn. Okay. So suppose I have a function of n random variables, and I want to establish the central limit theorem. So then the usual tool is to obtain the approximation in such a way that this one is a function. So this one is a function of single observation. And why this is useful? Well, and with zero expectation and finite variance. And why this is useful? Once you obtain, so you are interested in limiting this of this guy, but limiting of this of this guy is the sum of the two terms. The first term converges to normal by central limit theorem. Second term converges to zero. So some of the two terms will converge to normal. So that is the basic idea. And so this function basically characterized, right? This function. So you basically write, so the left side is a nonlinear function. The right side is a linear function of AXI. Right? So it is still nonlinear function of xi. It is still nonlinear function of xi, but linear function of AXI. Okay. Because it's so now you have just basically linear function, then you can do something. So then this function is so one thing we should note that this a function may depend on unknown parameter theta. So this function is referred to as influence function, and that's Hampel. He's a professor at Harvard and worked on some robust estimation at that time. And so he introduced the concept, and basically is how much. So what is the influence of a single observation on this estimator? So so then asymptotic properties of the asymptotically linear estimator can be summarized by considering only its influence function. So I'm not, okay, actually this is a definition. Okay. I'm not saying that this will hold any form, right? I'm not saying that. I mean, I'm not proving this one, right? It's just a definition. The definition of a particular class of estimator, which we call it asymptotically linear estimator. Okay. So the point is that if an estimator can be written as this way, then it's very easy to discuss the asymptotic theory. So that's the point. Okay. And many estimators actually of this form. End of the day. But how to find a function A is a tricky part. So, okay. So since A is zero mean and CLT tells us that, and so Slotski's theorem, we have this one. Okay, let's use this example to figure out. So this is a very simple toy example, right? So we have IID sample from normal, mu, and sigma square, and MLE of sigma square is just this guy. This is basically nonlinear function, right? Okay, then what is the influence of function of this? So, okay, so we want to, our goal is to find right? By the way, I should have this term is a P, so notation, right? So O1 is just a sequence, right? I mean, Cn, so this is a sequence, but for P1. So this is just a sequence satisfying converge to Cn to 0, right? So this is a notation for convergence to 0, but the P subscript T means that it's a probability limit. So I think this notation is used in calculus. I mean whatever analysis course, right? So this is a sequence of real numbers. So this sequence of real number has a literal 1 means it's a limit is 0. Literal P1 means that this guy is a random variable, and then the covariance is in the probability sense. Okay, so let's continue this with this. Okay, so how we, okay, then the idea is so we don't want the, okay, okay. so that we can make linear. And then so what is the order, right? I mean, okay, let me we know x bar converges to mu. So this one should be close to 0, right? In the middle. And then actually the order should be something like this. Converge to. So this will converge to something normal, right? So this should be bounded in priority. So okay. So that means we have a n minus 1. So this guy goes to 0, but in the order of 1 over n. Basically, if you take the expectation of this guy, the expectation will be 1 over n something. So you can see this. Okay. So then we can actually write it so this is influence function. So notice that if you take the expectation, this guy is a sigma square. So sigma square minus sigma square. So expectation is 0. That, I mean, right? In order for influence function should have a 0 expectation. So you basically we use this one. Okay. Basically what I did is to put it to here, right? To here. So this is sigma square. And then subset sigma square and take the root n both sides. And then you end up getting this. Okay. So let's move on. Okay. Okay, that's a good question. So in both sides, we're gonna take the square root, right? Root n, both sides. So root n here, root n here. And then you have a something called something OP root n times 1 over n. So that is actually 1 over root n. And so 1 over root n, big OP 1 over root n goes to 0. Okay. So we'll move on. Now we have some first result on the solution to estimating function. So this is the estimating equation, right? So suppose we have a solution, and we need some conditions, uniqueness of the solution. I mean, uniqueness, but let's forget about the technical details and say that we have a very nice function, and then end of the day we can express. You can find. So this is actually the influence function. Of psi hat. Okay, so this is influence function that you will obtain end of the day. So it's actually, so see, the point is, okay, I haven't explained this. Let me go back. I should have explained this more carefully. So this is nonlinear, very nonlinear, right? But if you can obtain this expression, we know xi is a IID. So x1, xn, IID implies AX1, AXN are also IID. That's an important result that we use to obtain the central limit theorem for this summation term, leading term. Okay, so that actually is placed same role here. So we don't know exact form here, but the point is that end of the day, it will be IID of this function, which because this one is a function of yi only, okay, and with unknown parameter, and this tau by the way is a partial derivative of the so we need a differentiation, but so that means to beginning with we are only considering some differentiable function, right, in the beginning. So let's move on. Well, I'm not going to talk about a lot of details, but here's a sketch of the proof of the result of this lemma. So you have a 0, right? But this 0 is this guy, and so you take the linearization, first order Taylor expansion, and then this guy turns out to be this guy is a sample mean, right? U hat is a sample mean of what? U psi 0 yi, right? So this is a sample mean of or some random variable, IID random variable. So then its partial derivative is also sample mean of the partial derivative function. Okay, so that means this guy is a sample mean. So sample mean will converge to the population mean in probability. So then you have this. And then we need to assume that this is non-singular. Then we move this one out here, right? And then multiply both sides by the inverse of this guy, you get the result. Okay. But in order for this to make sense, we need some conditions for the precedence. So that's this one is more difficult to show. This one is much more difficult, but once you show this, then you can do Taylor expansion. Well, okay, that's basically the very brief sketch. I'm not going to best what I can do. Okay. First, so here's several remarks. The first remark is that this lemma can be used to obtain a constant variance estimator, right? So basically, this is constant. This is a random variable, and so we compute the variance. Then we have a variance of u term, and then constant term should be estimated. So basically, tau, remember this tau is a population mean. So the population mean can be estimated by the sample mean, right? So that is basically the idea. And then we need to use estimate. So it's a function of unknown parameter. So originally, here you have a function of unknown parameter. So you need to compute plug in by its constant estimator. Okay. So this is a very popular form, and this formula is often called a sandwich formula. So this is ham, and this is bread. Okay, and sandwich. A second comment: this is not really relevant to this course, but maybe if you are doing some research, you may find this technique useful. I found it very useful in my research. So usually solving nonlinear equation is not easy. I have a lot of numerical problems in the end of the day. So for example, if you use Newton method, then you should, so in theory, right? In theory, this is Newton method and supposed to converge under some nice conditions. But in reality, it doesn't. It often fails to converge. Several reasons. First of all, sometimes this is not really where this could be non-singular in the true value. Okay, in the true value, in the limit, this is non-singular. But you don't know the true value, right? You are searching. So in your path, in your search path, the value could be singular, right? Or what is guaranteed in theory is that at the solution, in the limit, it is non-singular. And why we have such a numerical problem? Well, first of all, this is not symmetric. Okay, this is not symmetric. You have a, for example, okay, for example, you have a logistic regression. So, so what is the logistic regression? Yi minus xi beta, right? 1 xi. Well, sorry, logistic regression is a symmetric. So this is not really a good example. What else? Well, suppose, yeah, I think this is symmetric. Sometimes okay. You in chapters, in the non-ignorable means, so this is too much. But non-ignorable non-response, you have sometimes you use xi, ci. So in this case, xi, if you have a xi and yi, then it's a symmetric. But if you have a different one, then it's non-symmetric. Well, this is not really good example. We didn't. So anyway, we'll use this kind of example later in chapter 8. But the point is that if this is non-symmetric, then you have a good chance that the matrix is not really invertible. So to avoid some numerical problem, you can make it symmetrize. And one easiest way is that instead of solving this, you create Q function, which is a U prime U. And this function is now optimization function. So you, instead of setting to zero, you can find a minimizer. Okay, this should be much easier and much more stable than solving this one. Okay. So this, so, you know, quadratic optimization is better in terms of the numerical performance. So anyway, another comment. For the score function, yeah. Yeah, right. So this is actually becomes a GMM, right? Thank you. Yeah. So in the GMM, we even have some metrics, right? Weight metrics, and then you can optimize later. But if generalized method of movement, yeah. So okay, well, here the point is that here we already started assuming the just identified situation. You have a same number of unknown and same number of equations. So then these two solutions are equivalent. But GMM actually considers more suitable for over-identified situation where you have more equations than parameter. Then you can gain some efficiency. So if it's just identified, then the minimum will be 0, right? The minimum will be 0, Q function. But if it's not really, if over-identified, then the minimum is greater than 0. Okay. So the special case of the estimating function, scope function, then we already have this result, right? And that means this is actually the influence function. And the influence function is orthogonal to the scope function. So this, you can see that this influence function, right? So influence function times scope function is identity matrix. That actually is a very strong, have some connection with orthogonality because yeah, right, it's too much. So that's one implication. But anyway, so this is the scope function. I mean the influence function of the MLE. Now let's move on to missing data setup. So here we now have a missing data. Very general setup. And the parameter of interest is still phi, which is defined as a psi, right? Sorry, psi. Okay. So for this parameter, we have now missing data. Then how to construct an estimated equation where conceptually, right? This is, so you don't observe missing data. So you want to take the conditional expectation given the observed data. Okay. So that is so how do we know that this is okay? Well, important thing is that we want to make sure that any estimating function should have a 0 expected value at the true parameter. Okay. So then point is that if you take the expectation of this guy, and then you wonder whether this is 0. Well, the answer is yes, right? Because you basically have something like this. Psi 0 and y, and then conditional on y observed, right? And this. And so then you have end of the day, you have just the same. Right? By property of the conditional, so expectation of the conditional. So this is a marginal, right? Marginal of the missing data, right? Observed data, and then this is the conditional. So this is equal to this. And this one is 0. By definition of P0, right? So that means this is a valid expanding function as long as you correctly compute the conditional expectation. Okay. So this equation is called expected expanding equation. So this is so without conditional expectation, right? It is estimating equation. And but since we are taking the conditional expectation, we have expected. So 3E, right? E. Free. And also we already know that if S happen to be, I mean U happen to be score function, right? So if U is happen to be score function, then conditional expectation of the score function is mean score function, right? So that's already we know that gives the best estimator. So that's another, assurance of this approach. Okay. So now computing the conditional expectation in 7, it's not that simple, right? And because you have two problems, the conditional expectation depends on unknown parameter. So actually so you have should be lead. You have a unknown parameter here, and then this is the original, right, psi, and then this expectation involves unknown parameter. And then second thing is, even if you know the parameter, the conditional expectation can be has some numerical issue because you need to compute the integration. Essentially, this is integration. So here is one nice summary of the definition of the imputation. So imputation is just nothing but a Monte Carlo approximation of the conditional expectation. Right? So this is what you want to compute, right? This is what you want to compute. And you want to compute this integral, I mean, the conditional expectation by Monte Carlo sample. And then this Monte Carlo sample comes from where? Comes from prediction model, right? The imputation model. So predictive distribution. But between two schools, Bayesian school and African school, we have different choices. But the very concept, should be the same. So Bayesian approach, there's no parameter, right? They just everything is random. So then the parameter should be averaged out. So parameter is integrated out here. Frequentist, we need the parameter by, so we fix parameter by finding the best one, right? So we compute the parameter using the available information and estimate it and plug it into the model. So that is a frequentist approach. Okay, so we'll cover frequentist approach first, and then Bayesian approach. So multiple imputation. So chapter 5. So we'll cover this probably 2 weeks from today, something like that. Okay.
Similar to Bayesian optimization.
Yeah, right. So Bayesian, this is actually, so Bayesian imputation is exactly data movement. Well, actually, we should be very careful because in machine learning researcher is something different. So in machine learning researcher, data augmentation is actually creating some pseudo data to improve the learning performance of learning. But we are not really talking about machine learning in this class. Here, data augmentation. So what is data? Remember, data augmentation, Tanner by Tanner and Wang, that we covered in section 3.6, right, last week. This is basically keeps sampling approach. So we basically want to generate Y miss and oops. So basically we want to generate eta and Y miss jointly given observed data, right? And then we don't know this distribution, joint distribution, but we have a conditionally specified model. So conditionally, if we know this here, right? If we know eta, then prediction model is easy. And also if we know this imputation, then posterior distribution is easy. So that is the I step and P step, right? So that is the data augmentation. So basically, okay, that's very good. So this guy is actually P eta and Y miss given Y obvious and delta. So this is a joint distribution of this. So this joint distribution can be factorized as this. And we basically eta is eta is nuisance parameter. So we integrate out. Right? So this one we integrate out over eta, then we only get this distribution. So the actual tool for generating Y miss is based on our data augmentation. Frequentist approach, we don't have that level of sophistication. We just use MLE. Okay. Now,
So for the first agreement code, are there any fire? I think it's probably
yeah,
sampling code, right?
so to construct the posterior, you need a prior decision, of course.
Particularly on data.
Huh?
Prior distribution on data.
That's right. Yes. Okay, let's move on. So now here's so basically same thing. We have a parameter defined through this system function equation. So if there's no missing, then we just use it. But we don't have a full observation. So we basically construct so this third plot is actually imputation step, right? So we have a imputation, but let's suppose that we have because it's a Monte Carlo sampling, Monte Carlo approach. So let's use M Monte Carlo sample, right? We have a M Monte Carlo sample from this distribution and evaluated MLE. And then use that to construct the imputed estimating function. So imputed estimating function is based on M imputed values. I plug in, right, the imputed value, take the average. And we know that if M goes to infinity, then what? If M goes to infinity, it will converge to the conditional expectation, which is so this m goes to infinity. It will convert to triple E, expected estimating equation here, right? This is triple E. So point is that this is what you really want, right? This is what you really want. But to compute the conditional expectation, we do M imputation, right? We do Monte Carlo sampling. We do Monte Carlo sampling to approximate it. But then, tricky part is that we have a dependency on MLE. So basically, because of the Monte Carlo sampling depends on the parameter that we used to generate the samples. It has a dependency on a type MLE. Okay, so that is actually fairly difficult problem. I mean, it's a quite messy problem, right? And so this is not fully. So I think the first serious investigation is by Robbins and Wang, 2000, Biometrica. So this guy, James Robbins, if you Google James Robbins, he's at Harvard Biostatistics Department and Epidemiology. He's actually originally a medical doctor. He's an MD, a medical doctor, but he studied statistics as a hobby, and become a professor at Harvard. And so anyway, he's a real genius. So anyway, he seriously investigate this problem. So we'll formally study his theory next week. I mean, this Thursday. But I'm gonna briefly use an example to explain the concept. Okay, so remember, this is the right. You have when you compute the Monte Carlo sample, you have a dependence on MLE. So this is, you have a noises. So you are interested in estimating psi, right? But to compute it, you need to first estimate eta. So this kind of problem is actually quite happens a lot in statistics. So we can call it a noises parameter, in the sense that we are not really interested in estimating. Sorry, should be eta. So we are not really interested. So this is psi is a parameter of major interest, right? We are interested in psi, but to estimate psi, we need to estimate eta first. So that is this is a parameter of interest. This is a nuisance parameter. And so our goal is to find the influence function for this guy. So I'm going to use an example. So I have only 10 minutes, less than 10 minutes, but let's see. So remember, this is my regression imputation estimator. So now I have a beta hat estimated from estimating some equation. Okay. So now, how to find the influence function of the regression imputation estimator, right? That's the question. Okay. So we will use linearization, but it's not trivial, because suppose first of all, you need to write it this way, right? You express it, you express your final estimator as a function of noisance parameter, estimated noisance parameter. And then you take the you take the Taylor expansion around its limit. Okay, so you view this as a function of beta hat, and then take the first order Taylor expansion. Okay, then you will get the first line, right? The notation here, so I use nebula notation, which is first order tangent function. And so, I mean, this is column vector, so that means this is a row vector, right? But you can figure out. But the idea is to just the basic idea is to simplify the notation. So anyway, this is what we have. Okay. Now, the key part is what is this, right? What is this? So remember what is I beta hat? I beta at all in the very beginning. So this guy is what? 1 over 1 to n beta 0 plus beta 1 xi. That's it. So this is my functional form of the imputation estimator, right? If I plug in here, then I have a hat here. So that we know this is, so first thing to start is to determine the functional form and then evaluate its expectation of the tangent, right? Tangent. So you now take the partial derivative differentiation with respect to beta, and then take the expectation. Then this is what? 1, right? 1 and x bar. So that you have a expectation this guy. Okay. So remember, this is a two-dimensional vector, right? You have a two-dimensional vector, and so you have a rho. Okay. Now the question is how should I get rid of this? There should be an equation that defines beta hat. So we should utilize that. So there should be an equation, right? That determines which is this equation. So we should first identify which equation we have to determine beta hat, and then take the oops, sorry. So we have this one, right? We have this one, and then take the Taylor expansion. So that's exactly the same technique that I used for proving lemma 4.1 that I just did. So then you do that. Then what? Then same thing, right? Same thing here. And then what is the nebula? Tangent function of it. So this U itself is actually column. I mean, to the vector, right? U itself is a vector, and then you take the tangent of the two-dimensional vector, so it becomes a matrix. So let's take a look. What is the partial derivative of the this guy? See, so first line, you have a beta times delta, and beta times delta I times xi. So you have expectation of delta and expectation of delta times x. Same thing, denominator, I mean the second line, you have this guy, right? You have this guy. So you take the partial derivative of this guy, delta 0 times xi times delta, right? Delta xi. And then delta xi squared. So that is this guy. Okay. So you have two equations, one equation, two equations. So you basically here good news is that you actually have this guy, so that you can actually obtain right? Inverse U. Plus literal something. So that you can actually plug into here. So you have this solution and then plug it to here. Then you basically combine the two to get this solution. So that basically means is the result of the final linearization. So the linearization okay. So basically, right, we just so if you just stop here, 0.9, there's no hope because you don't know how to, right, handle this beta hat minus beta star. So you have to use another equation to combine to finally get rid of the beta hat minus beta star, and that's what you get here. So that is the linearization. So almost always, your linearization your linearization will be some linear convex linear function of the estimating function. And you have only to figure out how to compute this coefficient. And so this guy, Brender's actually come up with a very smart idea. He considered this kind of class. Okay, because he know the answer. I mean, we know the answer already. The linearization form should be this form. This expression, right? This should be the form of the final linearization. And you have only to figure out what is this correct C. So idea is that, okay, if this is a true linearization, then after you cannot linearize further because it's already linearized. So that means if you take the partial derivative, the coefficient should be 0 in expectation. So you use this one and then compute the expectation of the tangent function, set it to 0. That is your C star. So you obtain this equation to obtain C star. That actually is the another way of finding the linearization. So that's actually, in many cases, this one is easier to solve than the old way. I mean, but if you are interested, you can check more. But right. So the nice thing about it is that you don't have to, you don't have to compute the inverse of which you just view it as a equation. Okay, I think that's all. Yeah.